sure that you use a vehicle-specific wiring diagram. When we were doing research for Ford charging systems, we were surprised many times at how complicated those systems can be. Now we're going to show you 3 different charging systems, and Ford does vary slightly from those 3. They do, however, have some common areas. The alternator output goes directly to the battery on all systems. Another common area is Ford uses fuses or fuse links. Now in the top example we have a 75 amp and a 10 amp fuse in the alternator circuit. In the lower left hand corner example we have 3 fuse links. Now if these fuses or fuse links burned open, the alternator will appear dead, and hanging a new alternator on it will not fix the problem. So you have to test these fuses, and it's not that difficult. For this 75 amp fuse example, test at the large yellow cable. If the fuse is good, there will be B+ there at all times. And to test the 10 amp fuse in this example, test at the orange and yellow wire. If the fuse is good, there will be B+ there at all times. In fact, testing at the field circuit here, test both the 10 amp and the 75 amp fuse. So it's a one-step test. This is a system that uses fuse links. A quick step is to test for B+ at all times at the field circuit. It tests that single fuse link in the middle of the page there and the top 2 fuse links. So one simple test tells you that your fuse links are good, and you need to test field circuit voltage before you do anything else. Only after you have tested the field's B+ and you find that it's normal, or you've made repairs to make it normal, then you can continue testing. And you want to test the field current draw. And you're going to measure the field current draw with a low current probe around the field terminal. You can use a DVOM or a lab scope. Turn the ignition on, and current will go high for about 2 seconds. The meter is going to average, and we see 1.9 amps. And then in the lab scope waveform, we see a pulse that lasted about 2 seconds. Start the engine, and then we're going to get a lower amperage on the DVOM, and it's going to be an average. In the right-hand side there you see the waveform, and you're seeing that the regulation is starting to pulse. And you'll notice that the frequency of the regulation remains the same. Turn the headlights on and the blower on, and you're going to get a current draw pulse. It's well over 2.5 amps. Now the meter's going to average it, and you can see on the meter it's about 2 amps. But on the lab scope we can see the pulse clearly. Now look at the left side before the pulse, and then the down arrow pointing to the right side. You can see we start pulsing after that big initial load is applied. And what happens is with the lights and the blower on, we're going to draw more current. We have 0.8 amps. Without them on, we had 0.39 amps. In fact, when you look at this, you can see that the current was lower with no loads, and then when we added the loads, current got higher. And if you do notice that the frequency of the regulation remains the same. Now, we added a rear window defogger for a heavy load, and you can see we went over 2.5. We went to 100%, and it stayed at 100% for several seconds. The current draw should go over 2.25 amps for a few seconds. Here's 5 seconds, and then here's another full second. And then you will see the regulator start to catch up, and current draw drops slightly, and then it begins its pulses again. So use a heavy load and look for the maximum field current. A good regulator and good field brushes will have a draw of over 2.25 amps. Lower than normal current indicates that the field brushes or the commutator, the contact between the two, or the regulator is bad. Let's continue looking at different systems now. Many Ford alternators have this connector that has 3 wires in it. The 2 circuits will vary between vehicles. One will always be the field circuit. On some vehicles, they're communication circuits. And let's look at that. As you can see, the gray-yellow wire is our top trace. The light blue and the red wire is our green trace. The digital storage scope is grounded at the vehicle's battery negative. The top signal is from the PCM to the regulator, and this is going to set regulator voltage. This is the PCM telling the regulator what voltage it wants. The bottom circuit here is from the regulator back to the PCM, and it's signaling the charge rate. Now, the PCM says, hey, I want this voltage set at this point, and then this trace here, the green one, is telling the PCM, hey, this is what I've set it at. This is with no loads applied and a fully charged battery. You can see there are no commands on the top trace, the red trace, from the PCM, and there's some maintenance regulation voltage on the bottom trace. Now we apply a very small load. Battery slightly discharged after startup will cause this situation. So you start the engine up, the battery slightly discharges, and this is what you see normal. The PCM commanding the set point, and then the regulator with some intermediate pulses saying, hey, this is what I'm doing to follow your commands. And then we apply a large load. We took a 40 amp carbon pile tester and we put it across the battery. The PCM says, hey, this is what I want in the red trace. This is what I want for the set point. And you can see the alternator is working very hard to establish that. In fact, these pulses look a lot like that field pulse, doesn't it, that we saw in current draw for the fields. Now, other vehicles, these 2 wires are communication, but they're serial data communications. Now this is a image of a focus alternator, and in the lower right hand corner you see a gray and a blue wire. This serial data looks like this, and the way you get this image is connect your positive voltmeter lead to data link positive. That's the gray wire. Take your ground to your DSO and put it on a blue wire. That's data link negative. You do not ground the DSO at the battery negative, and you'll get these pulses. Now, right now we have a light load, but the battery's fully charged. Here we have a heavy load when we applied the 40 amps. Now it's very difficult to interpret serial data. So what you would do is analyze the signal with scan data. You go into your scan data, you pick up generator controlled duty cycle. And under this light load, it's 0. And then the generator signal field monitor, it's at 0.3%. So these 2 values are good for light load. Under heavy load, you can see that the values change. The duty cycle goes to 0.9, and the field monitor goes to 65.1. So no, we don't expect you to analyze serial data on a lab scope. Just go to your scan tool and read the duty cycle and the field monitor. Here's a simple circuit. The alternator is self-contained. It's very common to a Ford F-150. Now, the regulator reference circuit can help us diagnose the system. You can see we have that 3-wire connector, but you can see that one of the wires loop right back into the alternator to a separate terminal there. Let's look at this pattern by putting our DSO right here on the loop. We get this trace right here as we see. If you're using a DVOM, it's going to average 6.9 volts, 6.5 volts. It's going to average the voltage. And you can see sometimes the voltage is high and sometimes it's low, so the DVOM is just simply going to average that. But how do you use this for diagnostics? If this is an overall voltage check for the diodes, if the tops are not all even, some short, some tall, the diodes are bad. You would want to go to charging system test to continue testing. If the pulses are missing, the diodes are bad. Go to charging system test. Now, on this Ford F-150, we have a charge indicator lamp on the instrument panel. When this alternator is charging, it opens the ground for the charge indicator lamp. You can see that reading from right to left. We have a fuse, then we have the lamp, and the ground is what the alternator does. The alternator supplies the ground for this circuit. So when the alternator is not charging, it turns the lamp on. As a special note, during researching Ford's charging systems, we noticed that on some vehicles, mostly minivans, the value in the scan data did not match the actual system voltage. What we're saying is the scan data, as in this example, said 13.1, and a voltmeter across the battery said 13.9. Now, if you're using scan data for battery voltage and it seems lower than normal, stop what you're doing before you do any diagnostics. Put a voltmeter across the battery, and if it is 13.9 is in this example, then you're done. You do not have a charging system problem. So do not take the scan data, 13.1 in this example, and start diagnosing circuits and charging systems, because it may not be a problem. It's just a glitch in the software, and who knows why it's there. So make sure you know which system you're working on by using vehicle-specific wiring diagrams, and as you can see, it's not that difficult to test alternator circuits.